Today is March 14th, or 3/14, which is called Pi Day. And to celebrate, I'm calculating pi with just Redstone. This is my biggest and most ambitious Redstone project yet, so please enjoy. About 2 months ago, I started this project with one simple goal: calculate as many digits of pi as possible. And I was inspired by other pi videos that I had seen, such as calculating pi by hand by Stand Up Maths, with an NES console by NES Hacker, and even with relays made by the Science Elf. So, I wanted to do the same, but with Minecraft Redstone. There are many different methods and formulas to calculate pi, but I quickly honed in on 2 different methods: the Bailey-Borwin-Plouffe, also called the BBP formula, and an algorithm made by Stanley Rabinowitz and Stan Wagon. Both of these are something called spigot algorithms, which output 1 digit of pi at a time, perfect for my Redstone build. However, after a few days trying to figure out the BBP formula, I deemed it too complicated and too calculation heavy for Redstone. But it turns out someone had already done that method in Redstone, as I discovered this super impressive video by ModPunch3 using the BBP formula on his own Redstone CPU to calculate 361 digits. So, I decided to go with the Rabinowitz-Wagon algorithm, which I'm going to try and explain. You can skip to this timestamp if you're not interested. Basically, it uses this infinite sum, which equals pi, and converts it into this form, which is something called a mixed radix space. Now, instead of being a random string of numbers, pi can be calculated with just 2's and these fractions which follow a pattern. Before we get into the algorithm itself, I also have to mention how it calculates pi while only doing integer arithmetic. Basically, if you keep multiplying pi by 10, the digits slowly shift into the integer portion, allowing us to count it without dealing with decimals at all. And for this algorithm, we want the digit to be in the tens position and use the ones digit as kind of a blanket of safety, so imprecisions don't build up too much. To execute the algorithm, you first have to initialize an array full of 2's. This represents the 2's in the original expression, and each element in the array also corresponds to a fraction that comes from the mixed radix space. Unfortunately, this is where this algorithm's weakness comes in, which is that it requires a large amount of storage to store this array. Specifically, for n digits, you need floor of 10/3 n elements. For this example, we'll use 10 elements for just 3 digits. The first step is to multiply the whole expression by 10 to shift the first digit 3 into the tens place, which is where we will find it later. In the array, we just multiply each element by 10, which is the exact same thing because of distribution. Then, the algorithm can start to extract the first digit. Starting from the right, in the innermost bracket, when 20 is multiplied by 9/19, we can think of 20 as 19 plus 1. Distributing 9/19, we can cancel 19 with the denominator to become 1 and multiply it by 9. This effectively moves part of the original number out of the brackets while leaving the remainder inside, In the redstone build, this is as simple as doing integer division, moving the quotient out and leaving the remainder inside. Next, the 9 that resulted from the previous calculation is added with the next number, 20, and we can repeat the process of simplification like before. Eventually, when it reaches the first item of the array, we get our first digit 3 in the tens place. Now, we can get rid of it but keep the ones digit and redo the entire process again, multiplying by 10, carrying numbers, and we get the next digit 1. Do it one last time to get 4. We have to stop here because we would have needed a larger array to start with to make it more precise. In the real machine, the array is much longer than this example, 63 numbers long to be exact, allowing for up to 19 digits to be counted. If you want to read more about this algorithm, please check out this paper written by Stanley Rabinowitz and Stan Wacken. By the way, as a side note, I wrote a Python program to verify the algorithm before building anything with Redstone. So now, after walking through the algorithm, we know exactly what hardware needs to be in the machine. A giant array capable of storing 63 numbers, a multiplier to multiply by 10, an integer divider to calculate the quotient and remainder, a second multiplier to multiply the quotient by the numerator of the corresponding fraction, and finally, an adder to carry it to the next number. Extra components are also needed to control the whole process. And of course, we need a display so we can see what it outputs. Before I get into explaining each component, I want to thank Matt Batwings for his amazing Logical Redstone Reloaded course, which teaches you all of the basics of computational redstone. I learned how to build several of these components using these videos, and I could not have done this project without this course. For the array system, I made a custom design based on lock repeaters. The whole thing is made up of 63 modules, one for each element of the array, and each of them using 16 lock repeaters to store 16-bit integers up to 65,535. The modules are all controlled through some common lines that they can all access. For example, this white line controls the selected index. Every module monitors the white line, and when it detects a match with itself, the comparators in the module stop being powered from the side, allowing the signal from the lock repeaters to flow into the common output line. When a module is selected, it also gets ready to receive new data to be stored, which comes from this common input line. When a pulse is sent through this common black line, the selected module will briefly unlock its locked repeaters, allowing the new data to come in. For this build, we need 2 multipliers for different steps of the process. They both work by calculating the number n multiplied by different powers of 2. This is easy to calculate in binary because shifting a number 1 digit left is the same as multiplying by 2, similar to how the same thing multiplies by 10 in our normal decimal system. Then, we sum them up, for example 2n plus 8n to count 10n. For one of the multipliers that always multiplies by 10, we can simply hardcode this. But for the other multiplier, which must be adaptable, we count n, 2n, 4n, all the way until 32n, and we can enable and disable them to multiply by different numbers. In my opinion, the divider is the most complex single part in this build. Since division is basically just repeated subtraction, you need a lot of subtractors to make a divider, which would be way too big. So, I chose a design that only uses one subtractor repeatedly to save space. But the drawback is that the timings are a lot more complicated. This design is from Matt Patwings' old logical redstone series, but the original design could only divide 8-bit numbers by 8-bit numbers, so I had to modify it slightly to make it divide 16-bit by 8-bit. Ultimately, the divider became the limiting factor for how many digits of pi I could calculate. Unless I expand the divider, it can only output remainders of up to 7 bits or up to 127. If the divisor is 128, this is perfect because the remainders can only go up to 127. But if I make the divisor any bigger, I risk losing information during the division. So, given this limitation, how many digits of pi can we calculate? Well, the divisor in this integer division step comes from the denominator of these fractions that are assigned to positions in the array. Since the denominators are always odd, the maximum denominator, less than 128, is 127, which corresponds to the 64th element. This means that the maximum number of digits is 19 because it requires 63 elements in the array. The display's purpose is obviously to display the digits to the player, but it is also responsible for saving all of the previous digits calculated. It saves this data with a shift register, which uses locked repeaters. When new data needs to be inserted, the locked repeaters are briefly unlocked, causing all the old data to move over by one spot and the new data to move in at the very end. The data from the shift register is then fed into a decoder and encoder circuit, which basically just turns the binary numbers into instructions of how to display it, which is then used to display the number using a 7-segment display. This design is copied over to make 19 of them in total, and the beginning is slightly modified to add a decimal point and a pi equals sign using redstone blocks. The counter, which I will refer to as the binary counter, is used to keep track of the current index of the array while looping through it. I once again used a design from Matt Patwings from his Logical Redstone Reloaded series, but I made an important modification. Because we want to loop through this array, starting from the back and moving to the front, I inverted the output of the counter with redstone torches. So, when the binary counter is started at 1 and counts up, the reversed output starts at index 62 and goes down. As we have previously gone through, there are two main steps to calculating pi with the Rabinowitz-Wagner spigot algorithm. The first is multiplying every element in the array by 10, and the second step is going through the array to extract the digit, which I will call the carry step. I decided to make these considered two different modes, using an SR latch to do so. This solves a few problems, namely helping the machine decide which output to allow into the array at this junction, among other things. The main part of the control system is made up of these two redstone clocks, one for each mode because they take a different amount of time to run. Each clock is hooked up to a dropper with a certain amount of items in it, which counts how many iterations have happened and stops the clock at the right time. By the way, this dropper counter is reset when the corresponding clock is inactive, which is also decided using the mode system from the SR latch. Lastly, the clocks are connected to each other to form a closed loop with another hopper counter to count how many digits have been calculated. The control system also has a reset circuit which activates at the very start of the calculation, initializing the array to be filled with 2's, then setting off the main control loop. It also uses a similar redstone clock with a dropper counter. To understand the control logic better, let's walk through it step by step. This section is quite long, so you can skip to this timestamp if you're not really interested. In the beginning, when the player presses the button, the reset circuit activates. At first, it resets the index to 62, then sends the number 2 down the common input line of the array, and the redstone clock starts, each cycle decrementing the index until it reaches 0, and every element of the array has been set to 2. At that point, the dropper counter will be empty, stopping the reset circuit and sending a signal to the main control loop. Now, the signal decreases the main dropper counter, which counts the digits, by 1, marking the start of a new digit. The signal then goes to the SR latch, setting the mode to multiplication by 10, and after a slight delay, it starts the multiplication step. The index is again set to 62, and during each cycle, the data inside flows into the multiplier, then back into the array, before being saved into the same place. Then, the index is decremented, and the process repeats again, until every element has been multiplied by 10. After it's done, the clock's dropper counter will be empty, stopping the clock and changing the mode to the carry step and setting off that redstone clock. Similar to the previous step, the index is reset to 62, and in every cycle of the carry step, data from the array flows into the adder to add it with the carry from the previous iteration, which is set to 0 for the first iteration. Then into the divider. Now here comes the difference. The redstone clock also sends a calculate signal to the divider, which will start the divide process to calculate the quotient and remainder. That same calculate signal also branches off and gets delayed by a bunch of repeaters, just in time for the divider and the following multiplier to finish its calculations. The signal then locks the carry result into some repeaters to use in the next iteration. Meanwhile, the remainder flows back into the array and is saved into the same place it came from, before the index decrements and the whole process starts again. In the last iteration, the divider is actually set to divide by 10, to get the 10th digit as the quotient, which is the digit of pi that we want. This is then sent to the display, and at this point, the dropper at the redstone clock is empty, sending a signal which decrements the digit dropper counter, marking the start of a new digit, and also sets the mode to multiplication by 10 and starting that step once again. So, this process repeats for a total of 19 times, and eventually, the digit dropper counter becomes empty, and before the machine starts the 20th digit, the process is interrupted and the machine is fully stopped. So, now that you know all of the details about how the machine works, let's talk about the build process. The build actually went pretty smoothly for the most part, because it was mostly just building the components and connecting it all together. I managed to make it look somewhat organized, well, except for the control logic, which is just entirely spaghetti wiring. However, during the last few days, when it seemed like the machine was almost done, disaster struck. At first, there were some issues that I noticed immediately, and it all traced back to this single missing redstone dust that probably disappeared while copy and pasting. After that, I didn't notice anything was wrong because my first test actually went super well, although I stopped after a few digits because I didn't have enough time to run everything. Then, when it was time to run the machine for real, it failed at the 8th digit, outputting a 5 instead of 6. The mistake was actually caused by something super dumb. Like, just look at this. I somehow messed up the connections here so badly that one line wasn't even connected, and every other line above it was connected incorrectly. Anyways, I fixed that and thought I was in the clear because it actually generated a 6. But oh no, 2 digits later, it outputted a 7 instead of 3. This took hours of debugging because the issue somehow only appeared late into the calculation. In fact, it actually started at the digit 2, which is 3 digits before any errors were visible. I spent a long time trying to figure out why it wasn't working, but as it turns out, the divider, which I said had really delicate timings, only works when it gets a 10-tick pulse to start it. And I forgot that the pulse I used was actually 8 ticks. Finally, after fixing that, it was time to run the full calculation. Okay, so you might have noticed that there are only 18 digits here, even though I've been saying 19 digits the entire video. Well, it turns out I completely forgot how many digits were supposed to be generated, so I didn't put enough items in the digit counter. But it wasn't actually that hard to kickstart the machine again to calculate the final digit. The whole calculation took close to 25 minutes, running at the fastest tick rate my computer could handle. Previously, I mentioned that I had made a Python program that does the same thing, so let's compare it to that. REDSTONE built 25 minutes. Python program. Overall, I'm super happy that this ended up working out, and it genuinely took a lot of work to get this done. Anyways, I hope this video was entertaining and educational, and that it helped you learn more about math, REDSTONE, etc. If you enjoyed, please consider liking and subscribing, and leave a comment if you have any questions. Thanks for watching.